So we talked earlier in this chapter about water being amphoteric. Amphoteric means it can act as an acid or a base. And so even in pure water, water can do this with itself. So if you have one water molecule that acts as an acid and one that acts as a base, you can end up with hydronium ions and hydroxide ions. Now you might say, why would water want to do that? Well, it doesn't do it very much. It just does it a teeny tiny bit, but it can do that. That's called self-ionization. Water is ionizing itself. So it happens only to a very small extent. So we get small concentrations of the hydronium and hydroxide ions, and they're equal, right? So let's look at that again. I have two water molecules, one acting as an acid, one acting as a base. I get one hydronium and one hydroxide ion. So in pure water, there will be some hydronium ions and some hydroxide ions, and their concentrations will be equal because they are formed in pairs. Okay? So in pure water at room temperature, the hydronium ion concentration and hydroxide ion concentrations are equal to each other, and that value, that concentration, is 1 times 10 to the minus 7 molar. Very small. And this is where I wish I had done chapter 15 first. The ion product constant for water is called Kw. Kw equals the hydronium ion concentration times the hydroxide ion concentration. So if H3O plus is equal to OH minus, and is 10 to the minus 7, 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14. So we'll learn more about this ion product constant and what exactly it means when we talk about equilibrium in the next chapter. But this constant is true for water even when it's not pure. That if you take the hydronium ion concentration times the hydroxide ion concentration, it will always equal 10 to the minus 14. Now, hydronium and hydroxide do not always have to be equal when it's not pure water, but their product will be the same. So it's an ion product constant. The product of these ion concentrations is a constant. In a neutral solution or in pure water, those concentrations are equal. So in a neutral solution, the hydronium ion concentration is equal to the hydroxide ion concentration, which is 10 to the minus 7. If we add acid to the solution, that's going to cause the hydronium ion concentration to go up, right? Because acids produce hydronium ion. The hydronium ion goes up. If the product of these two is always the same, and this one goes up, the other one has to go down. So the hydronium ion concentration in an acidic solution is greater than 10 to the minus 7, the hydroxide is less. If we add base to that water, that causes the hydroxide ion concentration to increase. The product of those two has to remain the same, so if this one goes up, that one goes down. Does that make any sense? Blank stares. So this figure illustrates the relationship between these. So here we have the hydronium ion concentration just in powers of 10 and the hydroxide ion concentration. So if we add acid to the solution, the hydronium ion concentration gets bigger. As that gets bigger, the hydroxide ion concentration gets smaller. So you can take any of these, like we could take 10 to the minus 12 times 10, that's 2. 10 to the minus 2 times 10 to the minus 12, the product is 10 to the minus 14. Over here, 10 to the minus 5th, 10 to the minus 9th, the product is 10 to the minus 14. This one's getting larger, while this one's getting smaller. They're proportional. it's an inverse proportion. When one goes up, the other goes down. If the hydronium ion concentration gets smaller, then the hydroxide ion concentration gets larger. But you take their concentrations and you multiply them, it's always 10 to the minus 14. So let's calculate the hydronium ion concentration in each of these solutions. I don't think we need to do all three of them. So we're given the hydroxide ion concentration. The relationship that we need here is that the hydronium ion concentration times the hydroxide ion concentration is equal to 1.0 times 10 to the minus 14. So if we know what the hydroxide ion concentration is, then we can calculate the hydronium ion concentration. So we rearrange this equation. I'm going to divide both sides by the hydroxide ion concentration. Those cancel out. So the hydronium ion concentration equals 1 times 10 to the minus 14 divided by the hydroxide ion concentration. Here it's 1.5 times 10 to the minus 2. So you need scientific notation to do these. 1 EE negative 14 divided by 1.5 EE negative 2 would be 2 sig figs, 6.7 times 10 to the minus 13. And that's a concentration, so we're going to slap the unit molarity on it. So for the first one, we calculated the hydronium ion concentration. And the other question is the solution acidic, basic, or neutral? In an acidic solution, the hydronium ion concentration is bigger. In a basic solution, the hydroxide ion concentration is bigger. In a neutral solution, they're equal. So which is bigger, 10 to the minus 13 or 10 to the minus 2? 10 to the minus 2. When you're looking at the negative exponents, it can kind of mess with your brain. Because 13 is a bigger number, but it's negative. So this is larger. So we have hydroxide ion concentration is greater than hydronium ion concentration. These greater than, less than symbols, some students don't remember how to use those from previous schooling. This is the big end, right? It's open here. That's towards the bigger thing. This little pointy, tiny end goes towards the smaller thing. So the one on the fat end is the bigger one, and the one on the smaller end is the smaller one. So that means that this is a basic solution. Any questions? This one, just without even calculating, we can tell if that's acidic, basic, or neutral. Because in pure water, the concentrations are equal. They're both 10 to the minus 7. So this one's neutral. This one, it's the same kind of calculation as the first one. The hydronium ion concentration is equal to 1.0 times 10 to the minus 14 divided by the hydroxide ion concentration. And if you're using the scientific notation on your calculator incorrectly, you're going to come up with crazy wrong answers. So let's make sure that you're on the same page with your calculator before you take the exam. (1.2 times 10 to the minus 5). So which is larger, hydronium or hydroxide? Hydronium. So 10 to the minus 5 is larger than 10 to the minus 10. It's tricky. Because this one is and this one is 1, 2, 3, 4, 5, 6, 7, 8. There, it's easier to see, right? This one's bigger, more acid. This solution is acidic. Any questions?